And get started. Now that you all are back in conversation, I'll bring you back to me. Welcome to training session number 5. How do I have it listed in the program? I think it's training session number 5. Introduction to meta-analysis. My name is Josh Polanin, Dr. Josh Polanin, graduated a week and a half ago. Thank you. Doesn't get old, keep it going, all right. Thank you all for being here at my session specifically, but this is maybe the first time that I've spoken with some of you, and I just want to say thanks for coming to the conference in general. It's been a blast putting it together over the last year. I'm part of the local organizing team, I should say that, here at Loyola University Chicago. So it's been a blast putting it together the last year. I'm never going to do it again, so don't ask me. But I hope you're enjoying yourself, and it's going to be a fun evening and a fun afternoon. So, what I want to start out by saying is, at the end of the presentation, or the second half of the presentation, decided to give a little demo on software. Okay, so I see a lot of laptops right now, computer-savvy people. If you'd like to follow along step-by-step here in this room, you could go to these two websites right here, and I'll give you a minute or two to download this. It's a very easy process. You click on the download button and you can download it. Or these are streaming, obviously. We'll have them up on the web soon. This will all be made available to you so that you could download these programs and theoretically put in all the numbers and conduct a meta-analysis. But if you wanted to follow along with me, step by step, feel free. The first one up top there, both of the one on top, comprehensive meta-analysis, it's a free trial. So you could download it right now and use it for free. You just type in an email address and they'll zip it to you. RevMan, we'll talk about more about it in a minute. It's been built by the Cochrane Collaboration, our sister organization. Deals more with medical reviews, and it is completely free, so you can download it now and open it up and use it for the rest of your life. Would anybody else, should I wait 30 seconds so you can get down the email or the addresses, or does everybody have it who wants it? Yep. For you, Dave, I will wait 30 seconds.
And now when you said it was a free, I can now type the second.
Yeah, that's right.
That's why I was waiting for you.
So while we're waiting, I was going to mention this after my first act. Oh, by the way, I'm using a Prezi. Is everybody familiar with Prezi? I haven't caused motion sickness with any of my audiences yet, but if you are feeling a little bit, queasy, my mom has to sit in the front seat when we're driving. Maybe you should come sit up in the front row. I don't know if that'll help, or I don't know. Excuse yourself for a second, and I can send you the PDF version of this. Dave, you got it? Cool. On with the show. Okay, so I'd like to start off by saying that systematic reviews, and we'll talk about what that means in a second, but this is my view of systematic reviews. Systematic reviews are like this huge mountain here, okay? So it's obviously up on the screen. It looks like we've captured all of the information possible using a systematic review. But when we look beneath the surface, we find something that's actually quite large, right? And when we get to the bottom of the iceberg, we need a quantitative synthesis or a meta-analysis, okay? So what do I mean by that? A systematic review, well, let's start at the bottom. I was just talking to Lisa about this, and she reminded me, one of my co-authors and colleagues, Lisa De La Rue, wave your hand. Yep, I embarrassed her. Good. If we start at the bottom, and maybe you guys have been talking about this a little bit, you guys have heard of narrative reviews, right? Sort of the informal literature review. That's sort of the, in Campbell speak, or meta-analysis speak, review speak. That's sort of the lowest tier review that is possible, right? You just go out there and you type in some search terms and you get whatever comes back and you say, this is what the research world looks like. Sort of the step up, or it's a very large step up, is what we'd call a systematic review. And a systematic review, like I mentioned up there, are great. They pool together, obviously, a systematic search process and everything that you guys have been learning about. And they pool together all of the information within those documents, but they often leave out any quantitative information. In other words, they don't calculate an effect size. They don't talk to you about, they don't give you the information that David Wilson just provided you this morning. And so when we talk about a meta-analysis, quantitative synthesis, another word for it, that's when we calculate our effect sizes and then go ahead and pool them, which is what I'm going to talk to you today. So when I say that systematic reviews are great and they look like they give you the whole picture, what I mean is that if we dig underneath the surface area and we actually quantify some information, you can tell I'm a quant guy already, and we quantify some information, we might be able to explain the picture a little bit more clearly. Okay? So that's the angle that's my bias for the qualitative people who in the room. That's my bias right there, is leaning towards the quantitative information. Okay? I haven't made anybody sick yet, right? So let's just review the steps one more time. I realize that this is the 5th session. Has everybody, let me ask you this. Has anybody been to all 5 sessions? Have you all been to all 5 sessions? Wow, okay. So we're gonna try to keep this thing choppy as you guys are about to pass out from information, I'm guessing. But let's just, one more time for my benefit and for yours, let's just overview the previous steps that you all have learned about in the last 36 hours. A lot of information, okay? So, of course, Aaron talked to you, oh, that's a little bit miscentered. Aaron talked to you yesterday morning, way back at 10:30 yesterday morning, about problem formulation, right? And it really comes down to the purpose of your meta-analysis. Just like in primary research, I use that term to mean general research studies, i.e. not meta-analyses. So primary research is what I'm calling just a regular old study. Very difficult regular old study. You have to start with a purpose, right? So just like in primary research, in meta-analysis, you have to start with a purpose. You have to have some inspiration. You can see it up there. So that's the key, is to having a clear set of research questions and expectations for your research, right? Then, of course, you create a protocol. Wow, that's really miscentered. I wonder if it's at the screen, maybe. But we can figure out what that means. We create a protocol by creating inclusion-exclusion criteria, right, for which studies we're going to select. We want to identify the outcomes. And we come up with some timeline, and hopefully we distribute the responsibility evenly. I'm guessing Aaron talked to you a little bit about making sure that you don't do one of these things by yourself. Is that correct? Has that been thrown at you? Has that phrase been thrown at you at all? Okay, well, I'll say it for the first time. Do not start a meta-analysis or systematic review by yourself. It's a lot of work that you'll see, and you've probably seen over the last few day and a half. So make sure that when you're coming up with this protocol, aside from just doing all the things you would in primary research where you identify your outcomes and talk about your research questions, that you identify who's responsible for which task and create a timeline. Okay. So next, of course, you do the systematic search, and Karianne talked to you guys yesterday about that. She's great, and I'm sure she could give you a lot more information than even I am aware of. So make sure you follow her advice, and of course, start with a standardized search tool and locate potential articles. And then what's very important, which I am reminded of every time I do a systematic review, it's essential to contact those primary authors. Especially something we are not even going to talk about today. If you have missing data or if you can't calculate an effect size, even through David Wilson's great effect size calculator, you'd still want to contact those primary authors to make sure you could find all the essential information. Okay, then of course, Sandra Jo Wilson talked to you about extracting information, or coding, what we like to call coding. We create a code book, you train the coders, double code it hopefully, and then you extract the effect sizes. And then you get to the fun part, which is what I get to talk to you about today, what I like to do the most, and that's when you're close to synthesizing. So you've got all your studies in one, maybe Excel spreadsheet, maybe an Access, SPSS, whatever you're going to use. You have all the effect size information retrieved. It's very tempting to repeatedly synthesize your effect size and get a pooled estimate, but I would highly caution you about repeating your meta-analysis over and over. I would wait to do the steps I'm about to talk to you about here in a minute until after you've collected all of your information and you've calculated your effect sizes first. And so you want to make sure that you're almost completely done with that process before you start doing any of the fun, fancy statistics that I'm about to show you. And you should be able to convince yourself, if not others, at least yourself, that you've collected every study, every report, every piece of gray literature, every effect size that's available. We're looking for the population of effect sizes. Okay? That's the only way, really, that meta-analyses can be valid. Well, they can be valid, I guess, if you don't have every one of them. But you're going to bias your effects. You're going to bias your meta-analysis if you don't have every effect size collected. So you have to make at least every effort and convince yourself and hopefully others that you've collected all the studies that you need. Okay? That's not hard to do, right? Those 4 steps, you got this. Okay. So once you have your spreadsheet, so I've just gone over in 8 minutes everything we've talked about in the last day and a half, okay? It's, a couple months, maybe probably more like a year's worth of work that we've skimmed over. But you're finally done. You've got all your effect sizes. You're ready to finally do the meta-analytic synthesis. And I should say this, I say this whenever I teach Introduction to Statistics, or really any statistics course. I'm going to throw, I don't know, maybe 6 fancy looking formulas up on the board. They are not difficult. You can do this. Everybody in this room can do statistics in some form. This is pooling effect sizes is a relatively straightforward process. If you can calculate an average, we're going to take it one step further and calculate a weighted average. And I'll explain what that term means. But it's a relatively straightforward process. So sometimes, like my mother-in-law just got done with her intro to stats course for her EDD. I'm sorry, Rhonda, if you see this ever. And every few weeks she would ask me, for help because I'm her statistician son-in-law. And she would have a slight, she'd be, can I do this? And I have to say, you can do this. It's fine. Take it one step at a time. Convince yourself you can, and we're going to do that same process here. All right? Are we all on board? Okay, good. That's the kind of energy that we need right there. Okay, so a few steps to combining effect sizes across studies. So, of course, we're going to compute the effect size and the variance within each study. Then we're create a set of independent effect sizes. And then we get to the fun part where we compute that weighted mean and variance of the effect size, and then we're going to compute that 95% confidence interval and conduct the z-test associated with the effect size. Okay, so of course see David Wilson's presentation on how to calculate these things. We won't talk about the effect size since he talked about that a little bit. Now, creating a set of independent effect sizes, okay? This is a topic of much discussion. My dissertation focused almost solely on this slide right here, all 200 pages of it. Feel free to download it and take a look at it. But it's still a debatable question. What do we do when we have a study that has multiple outcomes, multiple time points, multiple treatment groups, multiple subscales? There's a number of different things that we can do. The key to meta-analysis, one of the assumptions of these statistics, is that you have an independent set of data points. So there's no, just like in, if you're familiar with multiple regression analyses or ANOVA, right? Every point, every person can't be represented, can only be represented once right? You can't have one person have multiple rows in your data set. That's the same idea in meta-analysis. You can't have more than one study represented in your data set, okay, essentially. So how do you get that? Well, this is what I talk about. Excuse me, I'm sweating a little bit. This is what I talk about quite a bit in my dissertation. There's you could split up your effect sizes into different syntheses, maybe one for each outcome. That's something that Lisa and I'm going to keep talking about our project since it's on my mind right now. That's something we've been talking about where we have a different outcome, we have a different synthesis for each outcome, and that way you have a completely independent set. Some people do what's called lumping effect sizes, where you actually take an average of the effect size within a study first. So if there's two outcomes listed in a study, you would actually average those first, and then you've got one effect size per study. No matter how you do it, and of course there's a lot more to be talked about here that we just don't have time for today. No matter how you do it, you have to make sure that you have an independent set of effect sizes. Now, I say all that, and I've spent a couple minutes talking about it. And down at the bottom, there's one caveat. There's a little bit of research. The methods assistant editor, Emily Tanner Smith, has been working on this a little bit. There's a technique called the robust variance estimation technique, which I will not talk about at all, other than to say what it is right now, and to say that there's a chance within certainly my lifetime, I think probably in the next few years, maybe in the next decade, that this whole create an independent set of effect sizes might go away, and you can actually use all the information within one study. So that's just to say that at the moment when you're doing it, I would try as hard as I could, or as hard as you could, to make sure there's an independent set of effect sizes. That's the most likely way to do it, but there's some more research coming that you might not have to. Okay, so you're all sitting there like we've spent 25 minutes and we haven't even seen an equation. So here we go. We're about to get to it. So now we've talked about how we get the studies a little bit, and we've talked about creating an independent set of effect sizes. Now what we need to do first, before we get into any type of synthesis and pooling, so what we're going to do is we're going to create a weight for each effect size. Now, what is a weight? Well, a weight just quantifies the magnitude that the effect size will have on the pooled effect size, the overall pooled effect size. What I mean by that is we want the studies that have the largest sample sizes, most often, to have the most impact on our weighted average. Okay? As remember, we're going after our last equation that I'll show you in this set of slides here is a weighted average of all of those studies into one effect size. And so it doesn't seem, and so the theory is that the smaller studies have a larger variance. There's a larger distribution of basically chance findings. And so we want the studies that have the largest sample size and in turn the smallest standard error to have the most weight in our calculation of our pooled effect size. Okay? And so I was thinking about this slide when I was looking at my slides earlier today, and I thought that I would just show you what I mean so that maybe you could get a better sense of this. So I just went back, and I'm guessing David Wilson talked to you about how to calculate the standard errors of each effect size, okay? And what we're going to end up doing is taking the inverse of the standard error of each effect size, and that's how we calculate the weight, and I'll show you that in a second. But what I want to do, so I can plant the seed in your head, is show you how you, just one more time, I'm going to write it down, the calculation of the standard error, we'll just go with Cohen's d, Okay, so you can see how much of an impact sample size has on the standard error. So if we look at the calculation of the standard error of D, it's, I know this by heart, I don't need to look at it, N1 plus N2. So the sample size of the first group plus the sample size of the second group over N1 times N2. Sample size of the first group times the second size of the second group, plus, and I'm running out of room, plus, and now here's where you've got the D, so this is your actual effect size of study I, over 2 times sample size of the first group times the sample size of the second group. And this is the standard error. And this is the thing, the output of this equation, the standard error, is the way that we calculate the weights. Okay, I'll show you in a second. So you can see as you increase your sample sizes, you're going to decrease that standard error. That's what happens. And so the studies with the smallest standard error, what ends up happening, get the largest weight in the effect size. Okay? And I'll just give you, I'll throw one more at you. If you were going to synthesize correlation coefficients, it's completely dependent on sample size, and actually its standard error of R is 1 over the square root of the total n minus 3, and that's the sample size, and that's the standard error. Okay? Oops, I'm going too quick. There we go. Okay, so I just want to plant that seed in your head. Okay? Let's see. I said all this. Yes, it does. So, the key is, so once again, before we get to the next slide, we want to use that weighted mean because the larger studies have smaller variance and it makes life a little bit more difficult. Now, before we get into how do you calculate the weights, or let me show, or when I show you the equation for calculating the weight, there's one more thing that we have to do. And that's decide which model we're going to use before we actually synthesize anything. And this is a fun way of saying that statisticians like to make your life more difficult. They make you choose a model before you even do anything. Okay, and it's key that you choose a model. Now, what do I mean by choosing a model? Okay, we have developed 2 different ways of calculating the weights, essentially. You can calculate using the fixed effects model or the random effects model. Now, there's literally an entire, last year we spent an entire hour and a half discussing what's the difference between a fixed effects model and a random effects model. So I'm going to spend 30 seconds on it right now and really confuse you all. Well, but the idea is, do you think you're going to estimate, with your pooled effect sizes, one single parameter where the effect sizes only differ by the sampling technique, sampling error, or do you think that you'll be actually estimating multiple parameters where the studies differ by sampling error and by some underlying characteristic that isn't explained just by taking the average of them? And so if you think you're only estimating one, this is what I say here, if you think you're only estimating one single population parameter, you choose the fixed effects model. If you think you're estimating more than one, you're going to choose the random effects model. And so what does that actually do? It changes the weights slightly. In a fixed effects model, when we calculate the weight, all we're doing, as you can see in the bottom of the left-hand column there, all we're doing is taking 1 over the variance component, which is the square root of the standard error. Square root of this thing. Okay? So we use a fixed effects model, we calculate the standard error, we get the variance, and we take the inverse of it, and that's our weight for each study. Okay? If we're going to use a random effects model, we have this term in here, tau squared. And tau squared is a little bit of a, it's a little bit of a bugger because it's difficult to calculate. And it's a long equation. And it's something that's a little bit outside of the scope of an introduction to meta-analysis class. But the point is, if you're going to conduct a meta-analysis, you're going to have to make a choice between a fixed effects model and a random effects model. And so these are the differences here. Now, all that being said, the next few slides, I'm going to use a fixed effect model. And it's mainly because it's easiest, but also because, no, not but also because it's the easiest. But I will say that in Campbell reviews, we often pressure or push review authors, the methods group does, to using a random effects model. It's a little bit more conservative. The standard errors are the confidence intervals are a little bit bigger. And it's just because you have, you're calculating the weights a little bit different. Okay? Okay, so, there we go. We're finally here at 145. Great. This is the all-important equation. So you've gone through, you've collected all your studies, you've calculated all of your effect sizes, you've calculated the weights for each effect size. Remember that 1 over the variance, or 1 over the square root of the standard error. And now you're ready to synthesize your effect sizes into one pooled effect size. And this is the calculation. This is the fancy calculation. Now, a lot of symbols, a lot of numbers up there. But all this is saying is, for each study, okay, for each single study that you have, you're going to multiply the weight of that study times its effect size. Okay? And you're going to add all that big number up. Okay, so if you've got 3 studies, you're going to calculate the weight, calculate the effect size, multiply that for each of the 3 studies, add that number up, and you're going to divide it by the sum of all of the weights, just the weights themselves. So mathematically, if you remember back to algebra, maybe back to high school or whenever, mathematically this is actually no different. This is equivalent to just the regular old average because the sum of the weights terms will cancel out on the top and the bottom. But for us, for our purposes, it provides the weighted effect size term. And so if we look, you think, well, Josh, I don't believe you. I need to see some proof. I don't just trust that you know what you're doing. I've done a little bit of a practical example here. Can everybody see this? At least a little bit? So I have 3 studies. That would be row 2, 3, and 4. And I've chosen to use Terry Piggott's last name, my name, and Emily Tanner-Smith, the co-chair of the methods group. And each one of those studies, let's say we are looking to increase mathematic test scores using some program. Okay, the most basic example that we could come up with. So you go into those studies and you calculate an effect size for each study. This is exactly what your spreadsheet could look like. You calculate an effect size for each study. It looks like for mine and for Emily's, we're getting positive effects, as you can see. And Terry's study is failing miserably. The control group students are doing better than the treatment group students. Okay? And now, so what I've done here is I've actually calculated the weight. So I haven't put in the different statistics. You'll just have to assume that I know what I'm doing and calculating the weights. And so that third column, the middle column, that weight column, is the weight for each study. So that's that 1 over the variance component, the square root of the standard error. Okay? So my study was the largest, so I have the biggest number in that weight category. So the Polanin row is going to get the most weight when we calculate that average effect size. Okay? So then the last column over is the effect size of each study times the weight of each study. Okay? And so this is the one that matters here. Okay? So we sum this term up and we get 7.446. So if we're following along with this summation right here is the, we'll call it the top part of the equation, just in case we don't remember what they're called. is the top part, so 7.446. And then, of course, the 0.391 is the sum. Nope, it's not. I don't have the sum of the weights on there. Does it silly of me? Well, we've got the sum of the weights. Oh, sum of the weights. 19. There it is, right there. Okay. I know what I'm doing. So if we take the 7.446 divided by 19, do a little bit of math, we come with our weighted average of 0.391. Okay? Now you say, well, that's all well and good. What would happen if we just took the average of those three studies? So this would be the unweighted average. This is sort of the non-meta-analytic approach. And you get an effect size of 0.107. Okay? So you can see, this is obviously an illustrative example because there's quite a big difference between the weighted and unweighted effect size. And the weighted one is pulled up by the large effect size and the large weight of my study. Okay? And that's it. That's meta-analysis. Okay, we all go home. Let's just take 5. That's we kid, but that's the essential part. There's no tricks here. This is the equation that that the computer is going to calculate, and that we're trying to derive. So that's the practical example. Okay, but once you get this, there's a whole lot more we can do with it. Okay, so the next thing is some policymaker or some, I should probably say some researcher or some astute policymaker is going to say, yeah, but what about the confidence interval around that effect size? Okay, so to do that, we have to calculate the standard error now of the effect size. So now we've had standard errors for each individual effect size. Now we're going to calculate the standard error for the pooled effect size, the weighted average. And to do that, it's simply the square root of 1 over the sum of the weights. So if we go back down here, it's a better zoom there. The sum of the weights again is 19, and the 1 over the sum of the weights, 0.052, and we take the square root, it's 0.229. Okay, so that's all well and good. What do we do with it once we calculate the standard error of that pooled effect size? Well, we can calculate the 95% confidence interval, and we can also conduct a z-test, just like we would any other analysis. So let's look at the 95% confidence interval first. Just like the 95% confidence intervals that you would calculate for a t-test or any other confidence interval, you're going to first calculate the lower limit of the effect size. You do that by taking the effect size minus that we usually use 1.96 times the standard error of the pooled effect size. And then, of course, you do the same thing for the upper limit. So if we look here for our example, the lower limit is 0.391 minus 1.96 times 0.229, and that's 0.058. Why do I think that math is wrong? I might have to check that. For some reason, I think that 1.96 is... Okay, that's all right. And the upper limit, we're just going to assume it is. And the upper limit is 0.391, that our weighted effect size again, plus 0.196 times 0.229, and that's 0.841. So that would be the 95% confidence interval around the pooled effect size. If we want to do the z-test, this is the statistical significance test of whether or not that effect size is different from 0. We can do that as well. Just like a normal z-test, it's the effect size, pooled effect size, over the standard error of that effect size. And for that, it's 0.391 divided by 0.229, and that's 1.707. We go to a z-table and look for the p-value, and we get a p-value of 0.088. We generally use the p-value of 0.05 as a cutoff. My dissertation focused on a little bit about this too, and I'll tell you the conclusion, which was I don't think we should be using a p-value of 0.05 as a cutoff. We generally conduct about 50 tests of statistical significance per meta-analysis. So type 1 error is quite inflated if we use this 0.05 cutoff. But at present, myself and only a few other people are talking about this. So you feel free to use the 0.05 as you would for anything else. You know, maybe in 20 years when we're talking again, then I'll have something else to say, but I'm the only one doing it, so. Okay, so we've covered a lot here. I want to stop just for a second before we go into the sort of the next step once we've calculated the pool factors. Are there any questions? Are there any questions about this very complicated procedure? Yeah.
So how can we, as highly statistical mathematical people, we can't be that way. How can we ignore the effects of repeated testing?
How can we ignore the?
Granted, it's so easy to do when you're trying to find something to show that your study is significant. After you have worked for years on this, you believe in it, you've done all this analysis, you've written it up, you want it to be significant. And yet, you in fact have done a lot of tests. So I'm wondering, what can we do to realize, hey, the biases due to repeat testing can apply to us as well as the people on whom we are meta-analyzing data?
Well, statistically, there are some ways that we can prevent bias. We can use multiplicity corrections, or we could simply stop using significance testing. Is that what you're getting at?
Yeah, I'm just saying that how can people do this as, as statisticians and researchers who are, and people really do care about research integrity. And so how can we solve this problem, basically stop the meta-analysis where we are at risk for false positive results? If we're doing all of those statistical tests, surely the likelihood of a false positive would increase.
I agree. We could stop conducting statistical significance tests.
Stop statistics as a whole.
No. I don't mean stop statistics as a whole. This right here is a statistical significance, a hypothesis test that we don't. I've argued in my dissertation, and we've started to talk about that we don't maybe even need these in meta-analysis.
Why not?
We already have an effect size.
But that's also not a perfect estimate. You can't.
No, I think what we could rely on a little bit more is this thing, this 95% confidence interval.
Yeah, I like, yeah, okay, so instead of having p-values, we have a confidence interval.
Yeah.
That, which is fine, it's another way of expressing.
Yeah, I think this is a discussion for maybe for a different time, and I'd love to hear your thoughts more on it. But I think there's a little bit of a different underlying maybe assumption or maybe underlying idea of using a 95% confidence interval. One, and two, I think if we could get people to use these, yes, you're still sort of backdooring a significance test, but you're getting a heck of a lot more information than you are just from a p-value.
If we simply publish the confidence interval, I think I would agree with you. But in fact, when people summarize, they say, oh, it had an effect on this, but not that.
Mm-hmm.
So that moves you from the conservative position of expressing the confidence interval to actually testing an hypothesis and coming out and making a positive statement about effect versus not.
Yeah.
And if you don't make that conclusion, no one will understand what your result is, and you have no policy. You can't communicate it to actual human beings.
Right. I agree with all of that. I think this might be a topic for a different time, but I certainly agree that we need to start thinking about that, and it's why I've been talking about it and why we've been talking about it quite a bit. Yeah.
Just the last point.
Yeah.
Why don't we do false discovery rate computation?
That is what I suggested. In my dissertation, I suggested using the false discovery rate direction. Yeah. So that was the conclusion that I came up with. Exactly. So yeah, let's talk after the session about.
Well, I mean, it is relevant here.
Yeah.
We don't want to just compute weighted effect sizes and CIs. We want to come up with a substantive conclusion
Yeah.
that will help people. So,
Yeah, I agree. I agree. And yeah. Well, let's talk after I could keep going on this for a few hours, but let's keep going with the talk, and we'll talk afterwards. I do want to. Is there any other questions about the actual nuts and bolts of weighting and effect size? Perfect. Okay, so you have your weighted effect size, and everybody's very happy, and policymakers and politicians are calling you and congratulating you on your hard work, but you have to tell them that you're not quite done, because you need to assess for heterogeneity among those effect sizes, okay? And so when we assess for heterogeneity, we're essentially asking is, are we estimating some common parameter? Or are the effect sizes different enough that there could be some underlying difference causing them to be different? Using difference 3 times in the same sentence. The idea, so we want to test, we're going to use a visual test and also use statistics to ask whether or not there's a common parameter or if there's some differences in those effect sizes, okay? So to do that, we can use a simple graphical test using a forest plot, and I'll show you a forest plot maybe for the first time for some of you. We calculate the Q statistic, and it's another hypothesis test, unfortunately. And we could also calculate the I-squared statistic, okay? So the forest plot just shows each study, the effect size of each study, the standard error of each study, and then that 95% confidence interval around each study. And so it's helpful not only for assessing heterogeneity, but just also as a visual to sort of interpret how our effect sizes look, sort of laid out in one nice, clear visual. Man. Okay, so let's look at it. So this is a forest plot that I've calculated from comprehensive meta-analysis. They build this as publication ready, so you could potentially pull this out and drop this into a publication. I have done so in a publication of mine, so I'm not saying it's a guarantee, but School Psychology Review was very happy with how this looked, so you could potentially use it in yours. And so, like I was saying, each study listed there. So again, the 3 studies, each row. I've got the Hedges G, the effect size, of course, the standard error around that effect size, and then a bunch of other statistics. And then each one of the studies is represented by a line up there. And that straight up and down line, the vertical line, is the effect size, and then the bar around it is the 95% confidence interval. Now this big diamond down at the bottom, that is the weighted effect size, the pooled effect size. Okay, so where the diamond, where the center of the diamond is the pooled effect size, and then the edges represent the 95% confidence interval of it. Okay. Now the way to test for variation graphically is simply to draw a straight line, try to draw a straight line vertically through all the 95% confidence intervals. If you can sort of visually draw a line that connects every one of those 95% confidence intervals, then you would say that the effect sizes are homogeneous. There's no variation between the effect sizes. But if you can't, you're saying that there's 1 or 2 or maybe a group of studies that are completely different from the average group. Now in ours, it looks like do I have a pointer? I don't have a pointer. In ours, it looks like we might be able to draw a straight line through. It's hard to tell. the first and second study where those two confidence intervals end. But we could, at the very least, we're going to say we're very close to having a heterogeneous set of effect sizes. Okay? So that's why we can't just do this thing visually. We are not single case researchers. Sorry to the single case researchers in the group. Any single case researchers in the group? Good. All right. Yeah. We're not single case researchers. We don't use visual statistics to calculate our effect sizes. So we will calculate the Q statistic. Okay. I have this long thought experiment, which I don't really want to try to explain to you at the moment. But the idea is, do our effect sizes differ more than just sampling variation? Okay, and that's what the Q statistic is getting at. That's what assessing heterogeneity is getting at. And that's what this lengthy paragraph gets at, which I don't really want to get into at the moment because we're running a little bit short of time. But these are the two equations for calculating the Q statistic. On the left is the original form, on the right is the computational form, just in case you would like to calculate the Q statistic by hand. Fortunately, we don't have to do that anymore. But it really is, if you think back to your ANOVA days, for those of you who are familiar with that, it's the same principled idea. Are the effect size different? Is one effect size different from the average? And far enough away that you can say it'd be different from, differ more than sampling variation would indicate that it should. Okay? And so the hypothesis test here is that all of the effect sizes are essentially equal. Okay? But there's no difference between the effect sizes. That would be our null hypothesis here. Okay? And we test the Q statistic against degrees of freedom of k minus 1, so the number of studies minus 1. Okay? So if we go back to our simple example here, we get the effect size of the weights, the effect size times the weight, and then I've calculated each one of those, the original form. Okay, so each one of these numbers represent each study. So we've got the weight of study I, or Terry's study, times the average pooled effect size minus the effect size of Terry's study squared. And then you sum that up and compare that summation, 7.012, to 2 degrees of freedom on a chi-squared table, and you get a p-value of 0.03. And so once again, our null hypothesis was that all the effect sizes are the same, or represent the same underlying distribution. So because that p-value is less than 0.05, we're saying that they're actually a heterogeneous set of effect sizes. That one of them probably differs from the rest of them. Okay. Now, there has been discussion, and some people have used, some researchers have used the Q statistic to justify whether or not they should use a fixed or random effects model. Remember I talked about fixed versus random effects models about half an hour ago? I'm telling you, you should not do that. And in fact, most people will say that to you now. The Q statistic is heavily dependent on the number of studies that you have. If you have a large number of studies in your meta-analysis, you have a lot of power to reject the null hypothesis. Therefore, you're very likely to say that your set of studies is heterogeneous. And so it's quite unfair to your model, to select a model based on this Q statistic. Now, you're going to go out there and you're probably going to read people doing it, and it's still used today, but you have a much stronger argument if at the beginning you can theoretically justify whether or not you've used a fixed or a random effects model, rather than just plopping your data into a computer and shooting out a Q statistic. Okay, so I want to make that clear. Okay, so, and of course we usually use p-value less than 0.05, and if we could get into that discussion one more time, because there's a lot of these going on as well, and you have to think very carefully about what p-value you're going to use as well. So there's one more way to assess whether or not we have a heterogeneous set of effect sizes, and that's the I-squared statistic. And the I-squared statistic uses the Q value that we've calculated, that we just calculated a minute ago. And the question it asks a slightly different question. It says, what's the proportion of the observed variance that reflects real differences in the effect size? So now we're looking at proportions, whereas the Q statistic just asked, is there differences among effect sizes? The I-squared says, what's the proportion of variance that's reflected in those differences? So the I-squared takes what the Q statistic is calculated, it does some fairly simple arithmetic, and it shoots out a proportion to you. This was created by Julian Higgins. He's a British researcher. It's a very recent statistic. This has probably only been around, I'm going to say 10 years and hope that none of you know the exact date. I think about 10 years, 8 to 10 years. So it's used fairly infrequently in education and psychology. And so we're just trying to get people reviewers to use it. But it is nice because it does give you this percentage where you can say, okay, so if you have a 0 to 40% I-squared, it's the heterogeneity is probably not that important. This is his language, by the way. If you have 30%, 30 to 60%, don't ask me why the percentages overlap. I don't understand that. I don't know what it means when you have 35% heterogeneity. This is Julian Higgins' mind at work right here, I guess. 30 to 60% though means moderate heterogeneity, 50 to 90% means substantial, and then 75 to 100 means considerable. So I guess that means if you have 80% on your I-squared, you get to choose whether or not it's substantial or considerable. I feel like I'm throwing Julian on the bus, so if Julian ever sees this, sorry to him too, but having a little fun at his I-squared. It's fairly easy to calculate. So our three studies had, what are we calling it? Either substantial heterogeneity. So we're in the sweet spot of substantial heterogeneity. With 71.3%. Oh. And so briefly, I don't have a slide in here. So this is my other thing I have written down on my notes for the conference. What does it mean when you have heterogeneity? That's one last thing that I want to discuss before we get into software. What time does this session end? I should know this because I wrote it, but 2:30? 2:15 it stops. Check the hard program. 2:30. Sweet. What does it mean when you have substantial heterogeneity? What does it mean when you have a significant Q statistic? Well, that usually means that it justifies conducting moderator analyses. Okay, so the next thing you would do is say, are there study characteristics that explain the differences, that explain the heterogeneity? Okay? I'm trying to think of a simple dichotomous. I've got one. We used to be very concerned, we're still concerned with publication bias. So one of the moderators that we check is where the publication derived from. Was it peer reviewed or was it not peer reviewed? Is it gray literature or is it in a published manuscript? So what you would do is you'd conduct a moderator analysis and you'd say, okay, what's the average effect size for the published studies and what's the average effect size for the unpublished studies? And if there was a difference, and a lot of the times just a few moderators will explain that heterogeneity. And so you can say, okay, there's a lot of heterogeneity among the effect sizes in the group that we have, but these study characteristics explain away those differences. And it's due to publication status or the percent of females in the treatment group or whatever study characteristic that you've coded. The point is when you have substantial heterogeneity, you have a significant Q statistic, that sort of gives you the right to conduct these moderator analyses. So that would be the next step. And moderator analyses was Ryan Williams presented on it yesterday at 10:30 in the morning. It's another one of those hour-and-a-half long workshops that we talked to you about. So we won't talk about it here today, but I wanted to make sure that we mentioned that. Okay?
Can I just ask-
Yeah, sure, go ahead.
I do have a question related to that. I mean, if you find that you have too much heterogeneity for your comfort, you do some moderator analyses. How do you not get into this problem of doing X too many number of tests to see?
Oh, gosh.
I mean,
We're
it's
back
a good
here
question.
again.
Yeah, but it's
Yeah.
a real question, though.
Yeah, it is. It is a real question. I'm going to promote my work. I've proposed some guidelines on what you should do.
You should.
Based on based on the number of tests that are common. So I've just said how many moderator tests do researchers usually use, and I've based my proposal on that. To my knowledge, there isn't a hard and fast rule. It's still sort of up in the air in terms of how many you use, but the caveat being, as always, the more that you do, the greater the likelihood of false positives, the greater the likelihood of type 1 errors.
I can see that there might be lots of different methodological things you could look at, study related, but there might also be lots of different intervention related.
There are, yeah,
things. So the number of things that you can look at.
are vast.
Yeah, exactly.
Vast. I had a study that I coded that conducted 950 significance tests. One study, one meta-analysis. A remarkable number of pairwise comparisons between a number of these different moderators. So you're exactly right. I mean, there's a lot of things that we're interested in. But I think a lot of it comes down to, in some sense, when we conduct a primary research study, we're faced with the same problem often. And so part of it's just researcher constraint at some point. I can propose all the guidelines I want, but at some point you have to have a theoretical basis. Should we conduct 5 more tests or not? I think that's still a debatable question, though. So it's not a question that I'm willing to put my neck out for at the moment, but you could read my dissertation and see what else I have to say.
John,
Yeah, Dave.
I like your comment about it being theoretical founded.
Yeah.
Is that's the way we should be doing even primary research as well.
Yeah.
I mean, if not, then we just go out and test everything we want
Mm-hmm.
and find whatever we get and say it's important. But what's kind of curious is our first talk in the morning this year talked about looking at these different studies and the process components and then creating narratives. And that may be a foundation for being able to think about what are the important moderating variables to consider.
Yeah. I think everything should start with that in mind, with the questions in mind, with a theoretical basis in mind. And in Campbell reviews, if authors, Lisa and I just dealt with this. If we proposed a number of different moderators to test, and one of the reviewers said, you didn't provide enough theoretical justification for why you're going to conduct those moderators. So we had to go back and say, these are the reasons. But this is just in the protocol stage. This is before we even did anything. So yeah, there has to be an underlying theory. But at the moment, it's still a growing area of research, and meta-analysis is still young. So I don't think we have the answers quite yet, other than it needs to be theoretical. Okay, so I want to move on because we only have about 12 minutes left. So I think what I'm going to do is skip by my funny jokes. There's a large supercomputer in what I think is the kernel. I can't stop. What I think is the kernel, maybe. This is how he came up with his secret recipe, I'm pretty sure. Fortunately, you don't have to use a computer like that anymore, and I have another joke, and I can't remember what it is. So we've only got 10 minutes, so what I'm going to do is I'm going to just briefly walk through it's really only 12 steps, 11 steps to calculate this effect size using comprehensive meta-analysis. And then I'm going to skip over RevMan for now. You've got the slides. It'll be up on the web. There's a number of different great resources. It'll just take me more than 10 minutes, and I don't want to rush through it. So you'll have all of this information. You can plug it all in. Okay, so CMA was developed. The first version was developed by Michael Bornstein almost by himself. in the late 90s, early 2000s, and then a team of meta-analysts got together over the course of a few years. Terry Piggott was one of them, Sandra Jo Wilson, David Wilson, all the people who've been talking to you. They all got in a room for a number of sessions. They all sat there and they came up with this comprehensive meta-analysis thing, and it was published in 2005, and it provides a number of different things. Just curiously, anybody download this while they were sitting here? Am I talking to? Oh, sweet, great, okay, perfect. So when you do get it, and you open up the software after you completely download it, I'm not going to use the tutorial. If you open it up for the first time yourself, if you guys use this, there's a nice little tutorial that walks you through step by step how to plug in all the information and run all of the analyses. I'm not going to do that because I think it's a little bit easier for me to just show you this way. Okay. So you get a blank screen. This is what it looks like, just like a normal packaged, like SPSS or something like that. And it's got a number of different little tools at the top. We're going to mainly use that insert tool. So the first thing you do, you say insert column 4 and you put in the study names. And that gives you a little study name column there on the left. This is my favorite part of the talk, by the way. I just look at the screen and talk to you about statistical packages. The next thing we want to do is tell it, give it a column for the effect size data. All right? And then there's a little boy who's looking at a computer making you feel bad because he can do meta-analysis. And apparently we can't. So he's just there to encourage you and also make you feel bad all at the same time. So there's a little button down there at the bottom that says show all 100 formats. Make sure you click that. You click next. You get a screen there he is again. You get a screen that says, okay, what type of studies were included in your analysis? And we're going to say there were comparisons of 2 groups or time points or exposures. There's a little tab that says generic point estimates. You could also put in proportions or rates. There's a number of different effect sizes. And just like David Wilson's effect size calculator, which I'm guessing he talked to you about in the morning, this will actually calculate the effect sizes for you as well if you just have the means and standard deviations. But if you've already calculated the effect sizes, you can use this just the same. So you get a little thing that pops up 2 groups or correlations. You click on the one that says continuous, because we're going to use continuous data. We're going to use the means. And then boy, that's hard to see on this screen. We're going to use the Hedges G one where we already know what the standard error is. And then he comes up again and says, are you sure you know what you're doing? And we go, yep, and we hit finish. And then you get this screen. Okay? And so a box comes up and says, okay, are you sure that you want to put the intervention and the control in these different columns? And you say, okay. And you get a screen that looks like this. So again, this would be if you had calculated your effect sizes outside of comprehensive meta-analysis. Okay, so you've used David Wilson's effect size calculator. You've calculated the effect sizes outside of CMA. So you're going to put in this, do I have a, yep. So you're going to put in the study names, the effect sizes in that Hedges G column, put in the standard error, and then you can leave everything else blank except for saying if the effect was negative or positive. And I'll just mention this one more time. If you did have means and standard deviations or a number of different summary statistics, F values, if you're calculating an odds ratio, you can use proportions and you can use a whole number of different things. CMA is set up to take that data. So you can type it in and it will calculate the effect size and the standard error almost automatically for you, so you don't have to worry about calculating the effect size somewhere else. Okay? Once you have all the studies in there, like I do there, you go up to Analyses and Run Analysis. And after you do that, there we go. I don't know why that slide's in there. Hey, there we go. The pooled effect size. So now CMA doesn't believe in justifying your model theoretically before calculating your pooled effect size. So it gives you the fixed and random effects pooled effect size automatically for you. So you have to be very conscious about which one you're going to choose beforehand, because it'll spit both of them out here for you. But again, you can see the each study with the Hedges G, the standard error, and then you've got a nice little forest plot, a kind of nice forest plot over there on the right. If you click on the next table button, which is up in the top left-hand corner, you get a nice looking output, and this will give you all the information that you would want to put into a manuscript, like the point estimate, the standard error. There's the z-value with the p-value again. And see, my math was wrong. It was negative 0.058 for the lower limit and 0.841 for the upper limit. There's the heterogeneity statistics, the Q value, exactly what we got, 7.012, the same p-value, and then the I squared of 71.477. This is the high resolution plot, which I mentioned to you back a few slides ago. You literally just one click away, you can see the button that says high resolution plot there. And it'll also give you nice, so this is a funnel plot, which I won't talk about more than to say this is what a funnel plot is. This is how you could assess for publication bias. And it has a number of different analyses that you could use for this. And then meta-regression and using moderator analysis is also an option. So now I'm worried about, I want to go to my summary, but I don't know how to, just look away for, can I do this? So I'm going to skip over RevMan, since we've got about 4 minutes, and we'll just do that. Okay, so conclusion, so systematic reviews provide part of the answer. This is what I'm saying. This is my bias. And meta-analysis quantify the effects. Okay? That's just the terminology. You'll probably hear people talk about them interchangeably. If I were going to talk to you, this is how we would talk. Okay? So first you calculate all those effect sizes and the variances. You decide on how you're going to handle independent effect sizes. You create the weight of each study from the inverse of the variance, the square root of the standard error. You synthesize those effect sizes using that very simple to use effect size calculation, weighted effect size calculation. And then you can create the confidence intervals. You can also test using the z-test. Then you can test for homogeneity, assess for heterogeneity, is the way I've coined it, and then enjoy it. And do I have anything else? Nope. And this is just an email that I'll leave up here for Terry, Emily, and I. And that's it. Any questions? Got about 2.5 minutes. If anybody has a burning 2.5 minute long question. Yeah. It'll be all online. We're obviously putting all of the video online as well, but the actual presentation itself will be up there as well, so you can click through. This is a Prezi. It's called a Prezi, but it comes out. You can create a PDF version of it that goes just slide by slide. It doesn't look as cool, but it'll give you slide by slide, and maybe it won't make you as sick sitting in front of your computer, too. So feel free to contact the methods group. Myself, Terry, or Emily, we're more than happy to help you out. And let me know if there are further questions. Enjoy the rest of the conference. Thanks for coming to my talk. Thank you.